So let me actually do an aside here. Definition of mass. There are actually two independent definitions of mass. And according to Newtonian physics, they both give you the same thing. So we don't have to worry about two independent definitions. So there's two independent definitions. Do you know what they are? Raise your hand. Okay. So one is the amount of stuff. In other words, what do I mean by that? We count the atoms and molecules. We count the nucleons. We count the electrons, protons, and neutrons. We count them up. And the amount of stuff that you have. That's the stuff mass. We just call that the stuff mass. I mean, that's not an official physics term, but it's the amount of stuff. Count the number of atoms. And we have a standard, right? And we do have a mass standard, which we talked about at the beginning of class, which is the kilogram, that bump of platinum in France. But we've very, very, very recently, within the last year, changed that mass standard to be something very different from that. But basically, on an atomic scale, we have a mass standard, which is, I believe, the carbon-12 atom. We just say that's got a certain mass, and so now we just count everything in terms of the carbon-12 atom, like how many equivalent carbon-12 atoms do we have, if we want to talk from an atomic scale. On a microscopic versus macroscopic. Microscopic scale, we can measure masses in terms of carbon-12 atoms. Macroscopic scale, macroscopic meaning something you can hold in your hands as opposed to microscopic, which is atomic scale. Macroscopic scale is kind of hard to count the number of atoms because there's so many of them. It's actually impossible. It's literally, I'd say literally impossible to count the number of atoms because you have so many of them macroscopically. How many atoms are in your phone? How many atoms are in the glass of water, in the bottle of water in front of you, right? There's 10 to the 30th. You can't count those. So there's a different mass scale for macroscopic when you're talking about the amount of stuff, right? Again, microscopically, we might talk about it in terms of the number of carbon, C12 atoms. Macroscopically, we might compare it to that lump of platinum in France. And that's our standard, mass standard. But it's just the amount of stuff. The second definition of mass is the inertial definition. And it's a different definition. It turns out the two are the same, at least according to Newtonian physics. I'll get back to that in a second. But the second definition is a body's resistance to changes in motion. That is also a definition of mass. And that's the inertial definition of mass. So this is the stuff definition. And what I mean by the stuff definition, again, is we're just counting the number of atoms, and that gives you the mass. But this is the inertial definition. A body's resistance to changes in motion. And it turns out that a body's resistance to changes in motion is proportional to the amount of stuff that you have. And actually, right, so when I say a body's resistance to changes in motion, how do you measure that? Right, mass is measured as the amount of force it takes to accelerate, force over acceleration, right? The mass could be defined as you exert a certain force, what acceleration do you get? You exert a certain force, what acceleration do you get? That tells you about a body's resistance to changes in motion. The resistance is the force, the change in motion is the acceleration. And that's where Newton's second law comes from, right? That's just Newton's second law, F equals ma. Okay, but anyway, there are two definitions of mass, the amount of stuff and the inertial definition. They're both the same as far as we're concerned, so we're not too worried about differentiating between them. Interestingly enough, when you get to relativity, Physics 251, next fall, for those of you who are taking it, we realize that those two are actually different. They're different, but they're only noticeably different when you get to very high speeds, speeds approaching the speed of light. Okay.
So now I want to show you a demonstration of inertia. Notice that this tablecloth here doesn't actually have holes in it. I'm using a green screen and there's green in the tablecloth, so it makes it look like it has holes. But this is an inertia demonstration you've seen before. I'm going to set up a bunch of dishes beneath a tablecloth, and I think you know what's going to happen. I do want to point out that this beer bottle is kind of cute. It's Edison Light Beer. Haha. So here I go. I'm gonna see if I had you here, I'd give you a chance to try it. But let's see if I can pull the tablecloth out from under the dishes. All right, I think I did a reasonable job. They just bounce a little bit. So why was I able to do that? How can I do that? It's not a trick, right? It's the fact that the dishes have inertia, right? They've got mass. I'm exerting a force on that mass. And now here what I have is a dish that has a lot lower mass. And that's a Newton's apple, by the way. The apple weighs 1 Newton. But that's beside the point. Okay, what happens? Look, the paper plate actually moves a lot more than the china plate. The paper plate has a smaller inertia than the china does, and so it's easier to move, right? So that, remember that inertia has to do with how hard it is to change a body's motion. So the fact that the objects have mass, the fact that they have inertia, I am actually exerting quite a large force on them. But that force isn't large enough to change their inertia. And actually it has to there is an additional factor here, which is a time factor, is I'm not exerting the force long enough to change the inertia. To change the motion, sorry, I'm not changing the inertia is the mass. I'm not exerting the force long enough to change the motion of the body. The inertia is high enough that I'm not exerting the force long enough. So there is a time factor, and we'll see more about that when we get to later chapters. But regardless, it's the fact that the dishes have inertia. If I exert the force quickly enough, it's still a large force, then I don't overcome the inertia of the bodies. I don't overcome their motion. Their motion, their tendency is to want to sit still, and they stay sitting still, even though I exert a force on them. So here I've got a second demonstration. It's actually very similar, but very different. It looks very different. I'm going to set up. I'm going to show you the setup. And here, the demonstration here is about eggs. Hence the chickies, and the fact that I'm going to set up the eggs in a situation, sort of like the tablecloth, where I'm going to put them on something and then knock the thing that they're on out of the way, yet the eggs stay where they are. But they don't really stay where they are because now they're suspended in thin air, and so they have to fall, hence the water for them to fall into. And I want you to think about what it has to do with inertia. What this has to do with inertia. It's a pizza pan. It's a little bit complicated setup. We got some toilet paper rolls, which are the egg holders. Got to center them directly over the water. The chickies are wondering what's going on. Little brothers and sisters haven't hatched yet. Carefully lining them up to keep the eggs safe. So now I'm going to, and again, there's a green screen behind me, hence the color is a little weird at times. These eggs are actually fresh eggs. They're not hard-boiled. This would work with hard-boiled, obviously, but I'm being really risky. Okay, and I'm going to take a broomstick and I am going to hit that pizza pan out from under the eggs. Actually, I'm going to do it a little bit differently, a little bit easier. I'm going to use it as a lever. I'm going to count down from 3. Boom, what happened? Pizza pan had to get out of the way of the broom. There was nothing it could do, had to move. Pizza pan, but the toilet paper rolls have the toilet paper rolls. I exerted a force on the pizza pan. It exerted a force on the toilet paper rolls. It exerted a force on the eggs. Here we go again. Boom. But the force wasn't exerted for long enough. The inertia of the eggs didn't move them forward, right? They had inertia, so they wanted to keep their motion. Pizza pan was hit out from under them. Did not overcome the inertia of the eggs until gravity took hold and pulled them down.